We have studied two types of DC machines, DC generators and DC motors. Now, when the machine is operating as a generator, then it is driven with the help of a prime mover. And when it is driven with prime mover, voltage is developed in armature. And this voltage circulates current through load. And therefore mechanical power gets converted into electrical power. Now same machine, when it operates as a motor, then it is supplied with electric current, and when current flows through armature, torque is developed which produces mechanical rotation, and electrical power gets converted into mechanical power. Now, during this energy conversion process, there are various power stages, and these power stages can be represented with the help of power flow diagrams. Now, these power flow diagrams or power stages is the most easiest way for calculating various losses and efficiency of DC machines. And that's why these power flow diagrams or power stages are very useful. In this video, we will learn power stages in DC generator and motor. Now here, first of all, you must know what are the losses in DC machines, which we have studied in our previous video. So you are advised to watch that video first for better understanding of power stages of DC machines. Now before studying power stages, let us first understand what is generator action and motor action and what is the difference between two. Now let us first see generator action. Now when the machine acts as a generator, then its armature is driven with the help of a prime mover. Now in this case, the input torque is T in. Now you know the relation between power and torque. Power P is equal to 2 pi n T, and therefore corresponding input power P in is equal to 2 pi n T in. In this case, speed n is in revolutions per second. Now when armature rotates, because of this prime mover, it cuts the magnetic flux produced by field poles, and therefore EMF is generated in armature. That EMF is EG, and this EG circulates a current IA in armature. Now when current flows through armature, it is a case of current carrying conductor placed in magnetic field. So it will experience a mechanical force, and because of force on armature conductors, torque is developed, and this torque is torque developed in armature TA, and according to Lenz's law, this TA is opposite to that of T in, and that's why it is also known as counter torque. Now the prime mover has to overcome this counter torque, and therefore some work must be done by the prime mover, and this work done by the prime mover for overcoming this counter torque, it is converted into electrical energy, and that's why mechanical energy gets converted into electrical energy. Now what is the power developed in armature? Now voltage developed in armature is EG, and current through armature is IA, and therefore electrical power developed in armature is equal to EG into IA. So electrical power developed in armature PA, it is equal to Eg into Ia, and again PA is equal to 2 pi NTA. Again in this case N is speed in RPM. So in case of generator, prime mover has to overcome the counter torque which is developed in armature, and when this prime mover overcomes the counter torque, then mechanical energy gets converted into electrical energy, and electrical power is developed in armature, which is equal to Eg into Ia. Let us now see motor action. Now when the machine is operating as a motor, it is supplied with DC current. Now here supply voltage is V and current drawn by motor is IL, and therefore power input, that is electrical power input to motor P in is equal to V into IL. Now when electrical power is supplied to motor, its armature starts rotating. Now when armature rotates, it cuts the flux produced by field poles, and because of that an EMF will be induced in armature. Now this induced EMF opposes the supply voltage V, and therefore the induced EMF in armature in case of motor, it is called as back EMF EB. Now the supply voltage V has to overcome the opposition offered by EB to circulate current IA. Now the electric work done to overcome the opposition offered by this back EMF, that work done gets converted into mechanical energy, and therefore electrical energy will be converted into mechanical energy. Now here the mechanical power developed in armature, that is PA, it will be equal to EB into IA. So PA is EB into IA because voltage developed in armature is EB and current through armature is IA. And again PA is equal to 2 pi n TA, where TA is the torque developed in armature, and again n is speed in RPM. So in case of motor, supply voltage V has to overcome the opposition offered by the back EMF, and therefore the work done to overcome this opposition gets converted into mechanical energy, and electrical energy will be converted into mechanical energy in case of motor. Let us now study power stages of DC generator. Now we have seen that how mechanical power is converted into electrical power in case of DC generator. Now here mechanical power input by prime mover is P in, and if input torque is T in, then input power P in is equal to 2 pi n T in. Now when the mechanical power is supplied by prime mover, then electrical power is developed in armature, and mechanical power gets converted into electrical power. We have studied that this electrical power developed in armature is Eg into Ia. But P in and EGIA, these two are not equal, because during this energy conversion some power is wasted in the form of heat. Now here there are mainly rotational losses, that is friction and windage loss, as well as there is core loss in the armature core, and therefore the difference between mechanical power input and power developed in armature is the iron, friction and windage losses. Means out of the mechanical power input, some power is wasted in the form of iron, friction and windage losses, and remaining power is electrical power developed in armature, and we have seen that that power is Pa, and Pa is equal to Eg into Ia, or it is equal to 2 pi n Ta, where Ta is counter torque developed by armature and n is again speed in revolutions per second. Now, when power is developed in armature, all the power here is not supplied to load. Again, there is loss of power. Now, this loss is loss of power in armature winding and shunt field winding, which is a winding loss or copper loss. So in armature there will be copper loss, that is Ia square into Ra, and in field again there will be copper loss, which is Ish square into Rsh. So this power is wasted in the form of heat. So out of EBIA, some power is wasted in the form of copper losses, that is armature copper loss and field winding copper loss, and remaining power is available to load, which is the output power. So remaining power is P out. Now here P out is the product of terminal voltage V and load current IL. So this is how in case of generator, mechanical input gets converted into electrical output through these various power stages. Let us now see generator efficiencies. Now you know that efficiency is equal to output power divided by input power. But that efficiency we call it as commercial efficiency or overall efficiency. But we can also define mechanical efficiency and electrical efficiency of generator. So first of all, mechanical efficiency. It is the ratio of B to A, that is electrical power developed in armature divided by mechanical power input, that is Pa divided by Pin, or it is equal to Eg into Ia divided by Pin. So this efficiency depends on friction and windage losses, and that's why it is called as mechanical efficiency. Then the second efficiency which can be defined is electrical efficiency. So it is the ratio of C to B, that is ratio of electrical power output to electrical power developed in armature, that is P out divided by PA. Now P out is V into IL and PA is Eg into Ia, and therefore electrical efficiency, it is equal to VIL upon EGIA. Now this efficiency, it depends on copper losses. And third efficiency, it is overall or commercial efficiency. So it is the ratio of C to A, that is electrical power output divided by mechanical power input, that is P out divided by P in. In this case, P out is V into IL, and therefore overall or commercial efficiency, it is equal to VIL upon P in. So unless specified, normally efficiency is considered as overall or commercial efficiency. Let us now study power stages of DC motor. A DC motor converts electrical power into mechanical power. In case of DC motor, electrical power input P in, it is equal to V into IL. So this is the input power supplied to the motor. Now, when electrical power is supplied to motor, mechanical power is developed in armature. And we have seen that mechanical power developed in armature, it is EB into IA. But again, electrical power input cannot be equal to mechanical power developed in armature, because in this energy conversion, some power is wasted in the form of heat. So here, when this electrical power is supplied, first of all, there will be copper loss in armature as well as in field winding. So some power is wasted in the form of heat as copper loss in armature, that is Ia square Ra, and copper loss in field winding, that is ISH square RSH. And therefore, out of electrical power input, that is V into IL, some power is wasted as a copper loss, that is copper loss in armature and shunt field winding, and remaining power is the power developed in armature, that is EB into IA, and it is equal to 2 pi n TA, where TA is the torque developed in armature and n is speed in revolutions per second. Now, the mechanical power developed in armature, all the power is not available at shaft, because again some power is wasted as losses. Now these are the rotational losses and iron loss in armature core. So out of the power developed in armature, that is EBIA, again the power is wasted in the form of iron friction and windage losses, and remaining power is available at output. So it is the power available at shaft, which is equal to P out, which is equal to 2 pi n TSH. Here TSH is shaft torque and n is speed in revolutions per second. So this is how, in case of motor, electrical power input gets converted into mechanical power output through these various power stages. Now similar to generator, we can define three efficiencies for motor, that is electrical, mechanical and commercial efficiency. So in case of motor, mechanical efficiency, it is the ratio of C to B, that is mechanical power output divided by mechanical power developed in armature, that is P out divided by PA, and PA is EB into IA, and therefore mechanical efficiency is equal to P out divided by EBIA. So this efficiency depends on friction and windage losses. Then the electrical efficiency, it is the ratio of B to A. So it is equal to mechanical power developed in armature divided by electrical power input, that is PA upon P in. Now here PA is EBIA and P in is V into IL, and therefore electrical efficiency is equal to EBIA upon VIL. And third efficiency is overall or commercial efficiency. So it is the ratio of output power to input power, that is the ratio of C to A. and therefore it is equal to mechanical power output divided by electrical power input, that is P out divided by P in. So which is equal to P out upon V into IL. Let us now derive the condition for maximum efficiency. For that, we will consider a DC shunt generator. So this generator converts mechanical power into electrical power. But during this conversion, various losses will occur in the machine. Now here the output power of generator will be equal to V into IL, because terminal voltage of generator is V volts and current drawn by load is IL amperes, and therefore P out, that is output power, is equal to V into IL. Now here there are two types of losses, constant and variable. Now the armature copper loss is variable loss, whereas iron, friction and windage, and shunt field winding copper loss, all these losses are constant. So here variable loss, that is armature copper loss, it is equal to Ia square into Ra, because current through armature is Ia and resistance of armature is Ra. Now here Ia is equal to IL plus ISH, and therefore armature copper loss is equal to IL plus ISH bracket square into Ra. Now here the shunt field winding current ISH, it is very small as compared to the normal load current IL, and therefore this ISH can be neglected. So if ISH is neglected, then variable loss, that is armature copper loss, it is equal to IL square into Ra. So here in this generator, variable or armature copper loss, it is equal to IL square into Ra. Now let the total constant losses, that is including shunt field winding copper loss, it is equal to WC. So WC is equal to constant losses and variable losses is equal to IL square Ra. So total loss is equal to WC plus IL square Ra. And you know that input power is equal to output power plus losses, and therefore input power P in, it is equal to output power P out plus constant losses plus variable losses, and therefore P in is equal to P out, that is V into IL, plus constant losses, that is WC, plus variable losses, that is IL square Ra. So this is input power and this is output power, and you know the equation for efficiency, and therefore efficiency is equal to P out divided by P in, which is equal to V into IL divided by V into IL plus WC plus IL square Ra. So this is the equation for efficiency of this particular DC machine. Now using this expression, we will derive the condition for maximum efficiency. Now to obtain the condition for maximum efficiency, let us first of all divide the numerator and denominator of this expression by V into IL. So dividing numerator and denominator by VIL, we will get efficiency is equal to 1 upon 1 plus WC divided by VIL plus ILRA upon V. Now for maximum efficiency, this denominator must be minimum. So this condition can be obtained by differentiating the denominator with respect to IL and equating it to 0. And therefore d by dIL of 1 plus Wc upon VIL plus ILRA upon V is equal to 0. So solving this, we will get derivative of this is minus Wc upon VIL square, and derivative of this is Ra upon V, and it is equated to 0. And therefore Ra upon V is equal to Wc upon V into IL square. So this V and V will cancel, and we will get Wc is equal to IL square into Ra, and therefore IL square Ra is equal to Wc. But IL square Ra is nothing but armature copper loss, and it is a variable loss, whereas Wc is the constant loss including shunt field winding copper loss. And therefore the condition for maximum efficiency is efficiency becomes maximum when variable losses are equal to constant losses. That is, when IL square Ra is equal to Wc, then efficiency will be maximum. Now IL square is equal to Wc upon Ra, and therefore IL will be equal to under root Wc upon Ra, and therefore the load current at which efficiency will be maximum. It is IL is equal to under root Wc upon Ra. So when load current is equal to under root Wc upon Ra, in that case variable loss will become equal to constant loss and efficiency will be maximum. Now this is a plot of efficiency versus load current or output power. Now when load on the machine is equal to 0, its output is also equal to 0, and therefore efficiency is equal to 0. Now when the load is increased, output power will increase and efficiency of machine will also increase. Now at a particular value of load current, variable loss will become equal to constant loss, and at that load current we will get maximum efficiency of the machine. Now if the load is increased further, efficiency of the machine will reduce. So generally the machines are designed such that when the machine is operating at its rated value, then its efficiency is maximum. Means near rated output, variable loss is equal to constant loss, and that's why efficiency is maximum. More efficiency means less operating cost. So for efficient operation of machine, you should note that the machine should be loaded at its rated value. Then only efficient operation will be possible. In this video, we have studied power stages of DC motors and generators. Now these power flow diagrams are very useful while solving numerical problems on efficiency and losses of DC machines. In our next video, we will solve numerical problems on losses and efficiency of DC machines. Thank you.